So I'm going to talk about kind of a related topic, if I can figure out how to make this thing work, which is this problem we call learn video querying. So the sort of motivation here, and it shares some things in common with what Mohammed is talking about, but the motivation here is a little bit, it's not video conferencing, but it's what we call video search. So the kind of vision we have is, imagine you have a big archive of video. It could be YouTube videos, or I'll give some more examples in a minute, and you want to find stuff in those videos, right? So you want to be able to have the equivalent of like a relational or a SQL query over this archive of hundreds of thousands of videos that you have stored for some, for whatever your purpose is. You want to search through all the lectures and find all the times that Sam made a stupid joke or whatever it is, right? So the question is, how could you build this? How could you build a system that does this? And what are some of the challenges that might come up if you tried to do this? So, some of the applications that we've been thinking about are these applications where people have large quantities of video that they might want to do stuff over. So things like traffic cameras. Maybe you want to find people who are, find particularly risky intersections where people run red lights a lot, right? Or maybe if you're dash cams, if you're an autonomous driving company, you want to find weird situations so that you can create sample video, or you can provide sample data to your autonomous vehicle that can help it to re-experience these weird cases, like there's a truck on the right side, or there's a bike going the wrong way, or something like that, right? So imagine that you could, or you're a biologist and you've got these wildlife cameras that are sitting there most of the time. Nothing interesting is happening, but occasionally a bear comes along and grabs a salmon, right? So these are examples of things that you want to detect in video. And wouldn't it be cool if you could just treat your video like it's a database and say, select from video where bear eating salmon, right? Like, wouldn't that be a cool capability if you had it? So that's kind of what we're trying to build. So we call this video analytics, and I gave a bunch of examples: debugging autonomous vehicles, traffic planning, real-time mapping, finding interesting events. These are all things where you might want to be able to run these kinds of queries over your archive of video. Okay, so why is this hard? I mean, maybe this seems like it's naturally hard, but if you've played with any of these recent machine learning algorithms, you're probably aware that, and this is an example of a screenshot from a thing called YOLO from, it's been around for quite a long time, but there are tens or hundreds of papers that are written in the machine learning community about this problem of essentially semantic understanding of images or video. Okay, and they're very good. You can take an out-of-the-shelf box, and it will, out-of-the-shelf model, and it will happily, show you things like, here's all the trucks, or here's all the people, and in fact, if you drive a modern car, for example, it has these kinds of models baked into it. If you drive a Tesla, it has this ridiculous visualization that even shows you what it's seeing. But all these modern cars have something like this that's inside of it. So what's the challenge? What's left? I mean, is this problem just been solved? And the challenge is that, yes, these algorithms are great at identifying objects in frames, but there's some problems. So first of all, video is very rich. There's a lot of video. And very, very many frames. So if you wanted to use, for example, a modern state-of-the-art, the best of these object detection models, they run at maybe something like 3 times faster than real time, right? So if I had a week of video and from 10 cameras, right, I would have to run these algorithms for something like a week times 10 divided by 3 GPU hours in order to process all of that video. So if I have a huge amount of video in the world, right, if I'm YouTube, or if I'm an autonomous driving company that has thousands and thousands of hours of video, it would be really expensive to do this kind of processing. Okay. Second of all, this picture here is just a single frame detector, but what I actually want to do is to ask questions across sequences of frames. And there are things that do this, these object tracking algorithms, but they're even more expensive than these kinds of basic algorithms, right? And then finally, we really want to build a system around this, right? We want to do interesting things on top of the video, like find instances of cars running red lights. I don't just want to find the cars or their tracks, but I want to actually say, where are all the cars that were running red lights? So how do we let somebody express something like that, right? right? And maybe SQL is the right way to do this, but SQL it's kind of hard to think about how you write something with a semantic expressivity, in SQL. Okay, so we want to run these types of queries that find individual objects, but more importantly, we want to track objects across frames. And the kinds of key challenges here are, okay, first of all, we don't need to look at every frame. Video is 30 frames a second, but cars don't move that fast. And we'd like to have these rich predicates, like we want to find red cars or red lights. And then second, we want to track objects across frames, and here the challenges are, we want to, again, do this without looking at every frame, so we want to do this without running these really expensive models and reduce cost. And we want to express complex conditions, like red light running. Okay, so the sort of framework for the sort of richer set of queries, this bottom object tracking queries, is something like this. Like, we want to have a sequence of detections of an object, and we want to think about objects existing, having some sort of permanence across frames, right? So like, from the point of view of an object detector, these frames are totally independent things, but we need to understand that they're actually this, white van or bluish white van that you see here that's making this right turn is actually the same across these 3 frames. And so what we want is some, essentially tracks of objects that are represented as, where each object is represented as a sequence of times, X and Y locations, and maybe bounding boxes, like the width and height of these bounding boxes. So this T(x1, y1) business is just saying there was this object, the white van, was detected at the following timestamps and locations. Okay, and so we can think of this white van as being represented not as these pixels, but as these sort of rectangles. Okay, and now the way we're going to query this thing is we're going to allow users to specify regions of the video that they're interested in seeing objects move through. So in this particular case, this is a fixed traffic camera. So we'd say, like, for this fixed traffic camera, I want to see cars turning right. Maybe I want to find all the cars turning right, so I can draw bounding boxes on this. So my query now looks like a bounding box, where I say, tell me all the instances of objects that pass through these 2 bounding boxes in sequence, red, then orange. Okay, and so my query is, this will allow me to find, vehicles turning, making turns. Okay, and then what the system will return is all of the instances of these paths that travel through these kinds of bounding boxes. Right? Okay, so we can do a bunch of things with this interface, like, we can do things like find cars that rapidly decelerate. So given a particular track, you can express this as a sort of a predicate over the bounding boxes and the positions of the vehicle. So you can find cars that are, slamming on their brakes as they come through the intersection. Right? Or you can find bears that are catching salmon by, looking at a sequence of video frames where, there's a bear that's, at some location, and then at some point there's an overlap between the salmon bounding box and the bear bounding box, right? And so we can express that as a predicate in this little language that we're going to build up. Or we can find instances of cars running red lights, because you can't see it in this video, but there's a traffic light that's up here that's in the you guys can't see it from the back, but I can just barely make it out here. There's a traffic light sort of in the top of this frame here. This is a frame from Japan, so cars are driving on the wrong side of the road. There's a kind of a famous traffic data set that people use. It's these big intersections in Japan that data is available for. So a lot of the examples that you see of traffic is from this intersection in Japan. So anyway, this is an example of a car running a red light, because this car is inside of this rectangle that is the intersection, and the color of the light is red at the same time. Okay? All right, so these are the kinds of bounding boxes that you would express. So what we've done is we built up this little language, the system called VAS, called Video Analytics at Scale, that allows you to express these kinds of predicates. And I'm not going to go through the details of the programming model, but the programming model is, it's not SQL, it's this kind of boxes and arrows of detections. And the different colors here represent different things. So they represent, the colors represent video inputs. The blue things represent transformations over the video, so you can do things like run a detector or run a tracker on the video. And then you can also write arbitrary little pieces of Python code that do interesting things like detect red lights or detect red cars. So you get a set of out-of-the-box, like computer vision models that you can run over these archives of video, and then you get an ability to write simple predicates in Python that allow you to filter out the things that you care about. Okay? And so we can compose these kinds of operations to implement complex things of the sorts of things that I've been talking to you about. And then you can apply these predicates to archives of video in order to get the answer. So you build up your pipeline, and then you point it at an archive of video, and it produces all of the videos that satisfy that pipeline. And so we've used it to do things. And so then the research comes up that we end up doing. Like this is, I mean, it's kind of a cool system, but the real research we think of is how do you do this efficiently? We've done a bunch of different work on essentially allowing you to avoid processing every frame and only focus on processing the parts of the frame which really matter. So for example, if you're only concerned with the bears and the salmon, you don't really need to look at the parts of the video that don't contain the bears and the salmon. So you don't need to run these expensive object detectors or trackers on the parts of the video that don't matter. And you can also learn the dynamics of the videos that you're looking at. So cars, for example, might typically be present for 5 or 10 frames in a video. And so you can learn over time that you don't need to process every video when you're tracking cars. You only need to process every frame when you're tracking cars. You only need to process every 5th or 10th frame, right? And so this is kind of an interesting learned systems problem. Like, you know, we're not really focusing on, we don't want the user to have to manually tune this to say only look at every 10 frames. We want the system to learn that the interesting stuff that they're querying about only happens every 10th frame. And so there's this learning problem that underlies the actual system that we built. Okay, so you can go check it out. vas.csail.mit.edu has some of our code and links to papers and other stuff like that. And we've done all these demos that I showed you. We've sort of implemented on these different types of videos. So tracking cars running red lights, doing this sort of counting vehicles, the kinds of things that people would do by hand, these traffic engineers where they'd count the number of people making a left turn to tune the timing on lights. You can automate that with this sort of dash cam videos, these wildlife videos, all these things we built little demos of them. I'm just going to show you one quick example of this red light running query. So this is the example that I showed you before with the white van entering the intersection when the light is red. And so the query looks like defining these 2 bounding boxes that define the region where you're interested in the vehicle. So we're looking for a vehicle that was first in the lower left blue region and then moved to the upper right blue region when this light was red. So we defined a little pipeline or predicate for doing this, and then we ran it. And if this works, this will show you sort of how the system works. I think we don't need this, but here's a little demo. So this was an example of the system pulled out this video. So you can see that the light there is yellow. It just turns red right there at that instant as this car enters it. So here's one example of a car that was in fact running a red light. And so the system has all these, so I can maybe play that. I don't know if you can see it play. It pulled out this video from this thing. So we're able to find a bunch of examples of people actually running red lights in this video archive. So you see there, that vehicle is running the red light. So anyway, it's kind of a cool system, and we think it's it's sort of this end-to-end. Sorry, let me just get through this. Sorry, the video thinks it's still supposed to be playing. Come on. Okay, maybe. Okay, all right. Okay, so that's the system that we built. I'll just say a couple more words about the kind of research that we're doing, these machine learning problems. So one way to think about this and is that what we've got is this tracking architecture. So this thing that's tracking these vehicles as they move through it. And these trackers have a whole bunch of parameters that dictate their performance. So when you're building a tracker, you have to decide how many frames at the rate at which you want to process frames. Okay, so that's one thing that again, like if a vehicle is present for 5 or 10 frames at a time, you don't only need to process every 5th or 10th frame. You also need to decide which parts of the frame to look at. So are you looking at every pixel or only a subset of the pixels? You also have to decide, and that's something you can learn over time based on the bounding boxes or where you find the objects that you detect. Maybe cars only occur in the pixels that represent the road, and they don't occur outside of that. So again, you don't need to process those pixels that don't have cars in them. But there's a bunch of other parameters you can tune, like the types of objects that you detect, or the resolution of the images that you do object detection in, and so each of these little gray boxes that you see here is actually a learned parameter of this video system. And what we've done is to build a machine learning system that's essentially trying to tune these parameters to the particular set of videos that you're processing. So as you process more and more videos from the same source, it learns over time what the right setting of these parameters should be in order to maximize your rate of getting the detections that you want to get at a minimized cost. And so this system is something like 30 to 100 times lower cost to process video at a very high accuracy, like in the sort of high 90s kind of accuracy rate. I haven't shown too many of these videos, too many of the evaluations here. I'm not going to go in detail into it, but you can check out our papers and look at it. Okay, so this is an example of a learned system. We have to, based on the observed object detections and query workload, we focus on identifying and tracking the objects that are in the most relevant regions of the video, and that's what we do the research on, all right? The other thing we've worked on a little bit is how to deploy these kinds of things in the cloud and how to build, because, for example, the object detections vary a lot over time. So this is, if you look at a video of some kind of an intersection, the rate at which you detect pedestrians in an intersection varies a lot by the time of day, right? And so the amount of work you have to do varies by time of day. And so you actually need to tune the rate at which you're doing these kinds of detections based on temporal features of the data. So we built this kind of architecture where we essentially learn the dynamics of the video over long time scales. So we call these sort of knob planning stage. So we look at the video for a few hours, and maybe we redo this every few days to kind of learn what are the overall kinds of dynamics that might occur in the video. And then we have this, what we call knob switching, where we, every few seconds, we look at the particular dynamics that we're experiencing. Like, are we in a high pedestrian or a low pedestrian setting? And we tune the parameters of the system based on that. And so the system can react very dynamically as the video itself varies. Okay, so just to wrap up, we built this new class of, there's this kind of new amazing capability that machine learning has unlocked, which is the ability to ask questions over video, right, to detect things in video. But when you just take machine learning out of the box, it doesn't actually solve the problem of like building a query system that allows you to process video, because it's very expensive, because it doesn't have a rich sort of interface that allows you to find the types of things that you might want to in video. And so in this vast system that we built, we're trying to sort of bridge this gap between what the machine learning algorithms provide and a real system for querying video. So that's what I had for you. Thanks very much. I have time for a question or two maybe, and then we'll do our panel. So thanks.